Sorry, I have a bad throat here. So I'm going to talk about implementing event-driven microservices architecture in F#. I'll explain what event-driven microservices architecture is. We'll touch down a little bit on F# also. Obviously, I can't talk too much because it's a talk by itself. So before getting started, I want to set the objectives of what my talk is all about. The first objective I have is I want to show what makes F# so awesome to implement such kind of architecture. And second, what are the kind of constructs that F# provides that actually aids you in implementing it, okay? So I'm going to start with introducing what F# is for those of you who don't know. I assume a lot of people would, but I'm assuming some people wouldn't know about F#. So F# is essentially a functional programming language for .NET. It's something like you have F# to C#, is something like Scala to Java, and what it is it takes the OCaml, which is another functional language designed by India and France, right, the core of the language, and it takes the object-oriented part of C#.NET and fuses them together. So it's essentially a statically typed language, right? You have static types, they are inferred, so you don't have to explicitly mark each type on your code. It's a managed language, so it runs on the .NET virtual machine, .NET VM, .NET CLR, and it's a functional language for .NET platform. So it has a somewhat declarative style rather than, as opposed to a prescriptive style, where you actually tell the computer what you're supposed to do. Descriptive style is more of where you describe your architecture, what you intend to do, what your program intends to do. It supports immutability. This statement is partially true, and I'll explain why it is. But generally, a pure functional language does not allow you to change a value of a variable once you assign it to it. I know that sounds bizarre for somebody coming from object-oriented language, because the very first thing they actually teach you is, you have variables that can change. But a pure functional language, actually, once you have assigned a variable to a value, does not allow you to change. Now, F# is not a pure functional language. And the primary reason why F# is not a pure functional language is it has to interact with C#, which is not a pure language. It has to interoperate with .NET platform. So it has to support all the .NET constructs in itself. So it doesn't enforce its immutability, but what it does is wherever you have a variable that is mutable, you have to explicitly mark that. And like functional languages, there are functions that are the building blocks. So actually, let's see what the characteristics of F# code is. So functions are the building blocks of a functional programming language. You can combine these ones to create higher order functions. So you could have something like, I have a filter that given an array, given a number makes yes and no decision, some kind of Boolean, and then I can apply this filter to a list of numbers. So essentially, I can create a function that would apply this filter and then filter out all the values for which the function, actual original function Boolean is false. Algebraic data types, we'll see some example of algebraic data types. For those of you coming from Scala background, Scala calls it as case classes, F# calls it as discriminated unions. So it encourages pure programming. Pure programming, like I mentioned before, is a style of programming where a function's output depends only on its input, right? So there are no side effects. Now, it doesn't enforce that, again, for the reason that it has to operate with the .NET language, but what it does is it makes it hard for you to write impure code. So you have to fight with the language to write impure code. And as a result of it, what happens is that generally people tend to write pure language. There are exceptions, mostly when you have to interact with other C# code, where you are forced to write impure code. So by making it hard for you to write impure code, you tend to write impure code only when you actually need it and not otherwise. And it has a support for pattern matching. I'll show some code examples for it. So there are some common resources for F#. I obviously can't cover the whole of the language. There are good books. Don Syme, he was the inventor of F#. So this book actually was written by him. This is actually a very good book. It's very concise. These ones are more for beginners and people coming from C# background. So before I go into the architecture of event-driven microservices, I want to touch upon why why is object-oriented language not the best language to implement microservices? And I'll dig into a little bit of a history. So when you look at object-oriented language, an object-oriented language has its roots in imperative language, right? You have C and Fortran, and then C became C++, and Java was essentially, and later on C# were all purified forms of C++, because C++ got really complex. So when you look at these imperative languages, they were designed to work on Van Neumann architecture. And Van Neumann architecture was basically a model of an abstract computer where you have a memory that can be thought as a state, and you actually manipulate that state. So in a very simplified form, Van Neumann architecture is a state machine, right? You transition from one state to another state based on your input. And object-oriented languages were essentially were designed for these Van Neumann architecture, but they brought in concepts like encapsulation, polymorphism, because what happened in the 80s, the software grew too complex. So existing languages like C and Fortran became too cumbersome, so there were more nice abstractions that were built on top of it to make programming more easy. And then what happened was that in the 90s, there was something called internet that came. And what happened with internet was it brought in new set of problems that were not foreseen before. And the two big problems that internet brought was portability and security. In an existing C++ code, right, I compile my code, I run it on one machine, I trust the vendor from where I got the code, or I wrote it myself, everything good. But when you talk about internet, you're running a code written by someone else that you may not be able to trust. So security now becomes a big issue, right? And if you have something like wild pointers in C++ that can just point to any part of your code, you could have some malicious intent happening in the code that you're not aware of. The second problem with internet was portability, right? You're sitting today, I'm going to bing.com, google.com, I have a Mac, some people might be accessing through Windows. I don't know what those servers are. Those servers could be Linux, it could be something else. Do I care about that? No, of course not. So portability became a serious concern because by definition, internet was supposed to be a connected set of machines that talk to each other in a common protocol, which is irrespective of the actual platform, actual machine that is being used, what operating system, what platform it is. Existing languages like C++ and others of the time, Smalltalk, etc., did not address these issues. So there was a refinement that was done, and that gave rise to what was called as Oak programming language. Oak was later on renamed as Java. Java was originally called as Oak, and it was basically a language designed for portable electronics. And later on, Microsoft wanted some language which is like it's not exactly a platform agnostic, but like a refined version of C++ that can run on a virtual machine. So they came up with C#. But the point I'm trying to make here is that Java and C#, the reason why they came was because the existing programmers of that time were familiar with object-oriented programming languages. And so Java and C#, just based on the paradigm that was existing, solved the current problems of portability and security. And as a result, object-oriented paradigm became the dominant paradigm. But there's something very strange about microservices, and I'm going to talk about it in details later on. But object-oriented programming models application as a state. But when you look at microservices, generally, they don't have states, because a microservice is a function, right? Think of Google as a function. It has an input, your query, just a string, right? It has a database, it indexes that, and it returns the value. Now, behind the scene, any kind of microservice architecture, you have like 50, 100, 1,000, I don't know how many microservices working. Each one of them acts as a function that takes an input and returns a value. There are some states involved, but typically, and I'll have a slide on it later on, but typically in a microservice architecture, your customer-facing services generally are stateless. There's a database back and there's some persistence on the back side, but generally that's how it works. And Imperative languages like object-oriented programming were designed for Van Neumann machines, but microservices are hosted on a cloud, and they don't interact with hardware. So they actually don't work, they don't really interact with Van Neumann style hardware anyway. They work on virtual machines. So that's the problem, is that you're using a wrong set of paradigm on an architecture which actually isn't really the kind of architecture that was designed for that programming language. That's the fundamental disconnect of using an object-oriented paradigm for implementing something like microservices on a virtual machine. And one of the things that people have a hesitation moving to functional paradigm is that, you have Java, C#, you have all the wonderful libraries, .NET, JVM libraries, and they have a very good ecosystem. But it turns out that most of the functional languages, like F#, Scala, they can seamlessly interop with other .NET or other JVM languages. For example, F# can call C# code, C# can call F# code, like pretty much seamless interoperability. The same is true for Scala in Java. So if you were to implement a microservice architecture, or for that matter, any code in F#, you have all the available C# libraries you can use. So it's not like you just have to use the F# code. The code, once that it compiles into a binary, into like an assembly, it has nothing to do with F# or C#. It's now a binary code that can be used by any .NET language. It could be F#, it could be Visual Basic, it doesn't really matter what it is. So now, let's actually see how would you model a service using an FP, right? So in services world, you have a service, whereas what functional programming gives you is functions as a construct, right? Like we talked about, functional programming uses functional as a building block. So you can model a service as a function, and in an event-driven microservices architecture, you have these events. And functional programming provides you the structure of algebraic data structure. We'll see some example of it, but ADT, algebraic data type, it can be used to model these events. The events are immutable. For example, I'm running a site like Jet or Amazon. Some user makes a request. At that point of time, that event has happened. There is no way you can go back in time and change that event. So if you look at events and plot it against times, events are immutable. You could probably cancel an order if you placed it, but that's a separate event. You can't change an event that has happened at that point of time. So in services world, events are mostly, pretty much all the time, immutable. And when you look at functional programming, it has immutability as a built-in construct. And then finally, most of the services tend to be stateless. So in functional programming, most of your code tends to be pure. It doesn't have any side effects. There are some exceptions. We'll see what those exceptions are. But what you see here is that functional programming captures the architecture of service world pretty naturally, in the sense that there are these physical concepts of services, of events, and they get translated to the functional construct 101, the mathematical or programming constructs that one is aware of. Anyway, so let's actually dive into event-driven microservices architecture and see how we can implement such an architecture with F#. So first of all, most of these services uses domain-driven design. We'll talk about what domain-driven design in details is, but mostly what it is it connects the implementation of your system to an evolving model of a design. Event-driven architecture, right? You have events that are happening, and your services react to that event. Event sourcing. Event sourcing is a technique that models the state of your system as a set of discrete events that actually can be combined to create the final state. And then you have microservices-based architecture. So let's actually examine each one of them in details. Domain-driven design. So domain-driven design is an approach for software development that connects your actual physical entities to a mathematical model or your programming construct. It's something you can think of. Domain-driven design is something that you do every day in object-oriented programming, right? you're designing a system, you're designing a banking system, savings account, customer. What you end up doing was you create a class in your code that corresponds to each one of these entities that exist in real world, right? So domain-driven design kind of works similar, that you have these physical entities and you actually create a model of this physical entity. So I have a customer, I have an account, I have like savings account, there could be different kinds of account and so on. So your focus of your code is actually on the domain itself, code domain and domain logic. And your design essentially evolves with the model of the system. And what it does is it allows the non-technical people or the business stakeholders to actually understand the code, because they understand the physical concepts. They can now map how the physical concepts actually are represented in your system. So we'll see some code examples of this one later on. But let's actually look at the architecture of how domain-driven design applications are. Typically, there are some variations, but this is like the most common architecture. Typically, how DDD works is you have a user interface, right? This generally runs in the client browser. Then you have an application layer. This usually handles the transaction. Then you have the domain layer, right? For object-oriented programming, people coming from OOP background, domain layer is what your classes would basically be, class hierarchy. And then you have an infrastructure layer or a persistence layer that usually would talk to your database. The bulk of your code actually stays in the domain layer. So how domain layer gets modeled in F# is domain layer has a concept of value objects, right, that are immutable. So F# would model these value objects as discriminated unions. And what F# can do is it attaches member functions to these discriminated unions, right? So you can actually do some operation and return a new object. So there's a anti-pattern in DDD called anemic domain models, which is basically essentially a class with just getters and setters. So you can avoid that by attaching member functions that actually operate on these domain models. So this is an example of F# code. It's a very simple example. So, sorry, you have a shape. You could have a shape of the point, polygon, circle, so on. So that's your discriminated union. So here you're representing all the different kinds of objects of the type shape. If you were to implement this in object-oriented programming language, you would start with a shape as an, class as an interface in Java, or an abstract class in C++, and then you start polymorphism and inheriting. This is how you would represent such domain models in F#. And here, you have an example of pattern matching. So you can operate on this domain model and you can match shape, and then you can say, I can create all these different kinds of shape, and then I can just list iter draw, and it will actually print this is a circle, this is a square, and so on. So that is how you actually apply domain-driven model concepts in F#. Okay. So now that we have talked about domain-driven design, let's actually talk about event-driven architecture. So think of event-driven architecture as reacting to events. So something happens in your system, and a new event is generated. Okay. All the listeners, would get notified in an asynchronous manner. Some may take action, some may not take. And it's kind of a highly distributed, loosely coupled architecture. And when I say highly distributed, the sender is not aware of the receiver. Sender does not know how many receivers are there. And it's usually used for asynchronous flow of information. You use event-driven architecture actually a lot without realizing it. A very common, maybe a dummy example of event-driven architecture is when you go to the airport, right, and you see all the announcements being made, flight ABC is about to leave, that's an event, right? The person who's making an announcement, he's the generator, he generates an event. Your message broker, Kafka often, is the air that transmits that sound. And your receivers are the people in the airport who actually receive that event. And some may take action in the sense if they have that flight, they will rush to the gate. Some may just ignore it if they are not on flight. But the fundamental aspect of this kind of architecture is the sender, the person who makes an announcement, does not actually know who the receivers are, right? He just makes a broad announcement, makes a broadcast, people would just listen. And how you, and another aspect of it is you can add and subtract receivers, or actually in this case, the collectors or people who, listeners, you can add and subtract anytime dynamically. So event sourcing. Event sourcing is a way where your state is modeled as a sequence of events, right? You could just store the event of that has happened, and then you can reconstruct that event actually and go back in particular time of history. A good example of event sourcing is your bank accounts, right? When you think about your bank account, I make a transaction in the bank, I deposit some money, I remove some money. Your total balance, which is the state of your account, is a sum total of all the events that has happened. So that's how event sourcing is. Version control system is an event sourcing system, right? Every commit is an event. And your total, the actual code, is sum total of all the commits that has happened over a period of time. Okay, so this is how you implement an event sourcing in F#. What you have is a fold function, right? You have events E1, E2, E3. You have an initial state. For example, in version control is like no code, absolute empty. In bank account, you open an account with $0. That's your initial state. And your current state is actually a list fold function that aggregates over all these states to create your current state. Fold function is sort of a functional programming equivalent of what a loop is. And the problem with this is that if you're building all the events from scratch, then there's a problem that there's a performance overhead. So you can take some snapshots and you can replace the initial state with a snapshot. So that kind of is a performance optimization that you can do. Microservices architecture. Microservices architecture is basically an assembly, is an application is composed of small services that work independently, and they communicate over a lightweight mechanism, HTTP, TCP for that matter, but mostly they are like platform agnostic. And the advantages is that you have independent releasability. So you have these services. You can scale up and scale down any way you want, right? If you have a application that consists of 1,000 services, you can scale up like 50 of them which are overloaded and not 950. So that basically gives you a way to scale in a more cost-effective way. If you have only one application, one service, you just scale the whole service up or down. Technology heterogeneity, you can have some services in C#, some in F#, some in another C++, Java, whatever you want. If one service fails, the rest of the services, they can still operate. So you have built-in resilience, and now you have ease of migration. If you want to port an application, you don't have to port the entire application. You can just do it part by part, one service at a time. So these are the various deployment patterns, right? You have request response, which is more synchronous. I give you a request, I get a response back, or you have an event-driven asynchronous that I have a broker, I just make a request and it's asynchronous in nature. I don't know what happened. The sender gets it, sender doesn't get it, I don't know. And typically in services, the tier 1 services that interact with customer generally are of the form request response because you need the resilience there, where tier 2, tier 3 generally are event-driven. Okay, so let's actually look at the functional programming view of microservices. A service is a function that takes an input and an output, right? So mathematically, it's y is equal to fx. This is a pure service, right? You don't have any database, you don't have any side effect. Logging is not considered as a side effect generally. And then you have, the non-pure service. So you see a database, you can think of S as a state. So there's an input state and there's an output state. So this is an impure service. And how you would implement such a service is you have your input type, you have an output type, right? And you define an F# function that takes this input and transforms it into an output. You obviously have something like an asynchronous way of communication. In asynchronous, what you do is you receive an order. You can place an order, you send an acknowledgement back to the user, and then you can send a second asynchronous call to a service on the back saying process this order. For example, you go to Amazon, you place an order, you get an acknowledgement back, I have received your order. Your order may not be processed right then. It may be processed at a later time. It actually sends an asynchronous response to the backend where it's put in a queue, and there it's processed, but you get an acknowledgement right away, so you know what's happening. So this is how F# would implement an asynchronous workflow. Okay, so let's actually get into the benefits of using F#. The first benefit you have is that you have like an infinite scalability. And the whole thing comes from immutability and absence of states. What blocks you in parallelization is often conflicting states, right? You have these locks, that you have resources, you have all these mutexes and so on. F#, because of its stateless nature and immutability, you can just practically scale infinite, right? That's your first big advantage. And that's actually one of the reasons why functional paradigm in general is really getting popular. And the reason is that Moore's law sort of hits its limit, right? You would not have faster, maybe not processors, I'd say, but faster cores. You probably won't have it. It used to be like you would double the speed of your core every 2 years. So now if you want to increase the speed of your application, or you want to have a better hardware, you basically have multi-cores. So you would just, you would just have multiple cores that can process the same application. So you want to have a kind of an application which is easily parallelizable. And that's what function programming gives you. Since it does not have states, it can process these requests in parallel. So you can have n number of states, and still your application, as you increase the number of cores, your application performance would increase linearly with the number of cores you have. Productivity. So F# code tends to be a lot shorter than C# code. And there are some numbers. I've actually taken it from a project that was done in the UK. And you see that there are F# lines 1436 that compares to 4610 and so on. The graph actually is better. It shows how compact the code is. And what productivity does for you is it's less lines of code you have to write, so you can faster time of market. You have, your developers would have less ramp up time because they have to read less code. There's a very common criticism of functional program. People who tend not to move to functional programming is they say that it's hard for us to hire functional programmers. And I find that argument silly. And the reason why it's silly is, while I agree with you that it is hard to find a functional programmer as opposed to an object-oriented programmer, but a functional programmer has to write 5 times less code than the object-oriented programmer, which means I have to hire 5 times less. Even if I find like one guy, I can still have him do the job of 5 people that are five C# programmers, right? So that argument is somewhat flawed in my nature. Code correctness. So what you have is you have strict typing, right? You have strict typing, unlike dynamic languages like Python. So your code tends to be more correct. But what F# particularly does is it has a type inference system. In fact, it's called Hadley-Miller system, that you actually don't have to specify the types. It actually infers it from your code. So for example, I have a function, I'm defining it on some variable x. That function is defined on integer, and then I use it on a variable, right? And I don't define that variable as integer, but F# would know that this variable is integer because the function was defined for an integer. So it kind of infers it. So you have like a best of both worlds. You don't have to specify types, which makes languages like Python very efficient, or actually less typing, less verbose. But at the same time, you have type safety of languages like Java and C#. So you kind of have the best of both worlds. Immutability makes code more predictable. Why? Because you don't really have states to worry about. Your function, the output of a function only depends on its input. There was I used to work for Microsoft, and one of the, I think they make you do a training, introduction to C#, and there was a joke that instructor said, what are the 3 causes of bugs in program? Memory, memory, memory. Okay? And what memory is memory is a state, right? So when you say a bug, what exactly is a bug? your system enters into a state that you did not account for, that you weren't expecting that it would enter, and it doesn't know how to handle that. So it crashes. Right? That's what a bug is. Why did system enter into that state? Ideally, you want to prevent the system from entering into such a kind of state. But what happens with an object-oriented programming language is, let's say you have a simple application, right? You have 1,000 classes, and each class has 5 integer as variables, like very simplified view. So in total, the possible number of states that your system can enter, and each variable, let's say, is, for simplicity, I would say it's a 2-byte integer, right? So the possible states the system can enter is 2 bytes into 5 raised to power 5,000. Whatever that number is, it's a big number. That's the possible states that your system can enter. And it is impossible for you to account for each and every state because there are so many states, right? So you have all the constructs like assertions and checks to prevent that. But it so happens that you skip those. Sometimes you don't expect a system to enter a certain state, and it does. And that's what causes a bug. So what immutability does is eliminates that whole class of problem. Once I have assigned a state to a variable, I can't change it. That's it. So, and what it does is it has list fold function that we thought, and it has all the kind of various functional constructs. So you can do all that in object-oriented programming in F# using those constructs without actually mutating the variables. And then it has an exhaustive pattern matching. So we saw the example of pattern, right? Various kinds of shapes, circle, polygons. And you can do a pattern matching on these shapes. And what happens is that if you forget to account for one pattern, your code would not compile. So a lot of errors that would otherwise happen at runtime, it actually got caught at compile time. There's a joke in F# community that if your program compiles, it probably runs. In the sense that most of your problems would actually be found at the compile time. So if you've gone through the compilation, you've kind of eliminated most of them. And then you have the type system. What type system does is type systems like discriminated unions, it makes representing those illegal states impossible, right? Because you can have a circle with certain parameters, shape, and so on. And what it does is it limits the possible number of states that your system can enter. Like we saw in object-oriented programming language, right? You have 1,000 classes, you have 5 variables, the number of states is 5 into 1,000. Here, you're cutting that number by a big chunk because you have all those states that your code would not even enter because your type system makes it illegal. If you do something like that, the compiler will tell you right away. So let's talk about testing. What makes these services easy and testable? So in a typical request response section, right, we see these services, and most of the services are pure services, so they don't have database attached to it. And pure services are very easy because since you don't have a state, I can exhaustively test these pure services, right? My output of this service depends only on my input, so I can just exhaustively test. I don't have to worry about breaking them. With impure services, there is a little bit of unpredictability. And when you actually design your application, what you generally tend to do is you tend to move as much code as possible on the pure side and as little code as possible on the impure side, because you can test your pure side really well. So for example, with an impure service, you're running an e-business and one of the service bills your credit card. Now that's impure service, right? Because there's a state change, a customer is billed. So you would just have that one service that bills the customer, and you can test this, okay, I can bill the customer $5, $10, $20, etc., etc. And everything else, the logic of how that value is computed is actually moved on the pure side of it. Because you don't want to bill a customer 200 times during your testing, right? That's going to be awful. Same thing you can do with testing microservices in event-driven. The problem with event-driven is that the sender does not know whether the receiver has received or not, right? It goes into this message broker, which is kind of a either. So there, what you do is you identify these services, and you can have dummy test drivers and interpreters that can inject the message and then read the message when the order service actually processes. So that way, you can test the event-driven architecture. So that's all. Questions?
Thanks a lot about this talk. If you have a question, please raise your hand. Okay, let's start.
Hello, thank you. Thank you for the talk. So recently I had actually a good experience using this approach to build a microservice, event sourcing, DDD, like immutable objects. And now I'm kind of tempted to put it everywhere. So my question is, how to decide when to use functional approach for microservice and when not to?
Okay. So obviously, I can give you an empirical answer to that. I don't really have a hard and fast because it's a little bit of a judgment issue. Yeah. So I would say that think of it as where you have, think of your mental model of what a functional programming does, right? You have an input and you apply transformations at that input. So if your program fits in this mental model, it's a good candidate for functional programming, right? And if your program fits in a model where you have a central state and I just manipulate that state all the time, then it's a good candidate for C#. So I'll give you an example of a good candidate for functional programming, compilers. Actually, ML, on which F# is based, actually was written for all the static analysis and compilers. It's actually still, compilers is a very good application of functional programming because think of what compiler does. A compiler is a function that takes a string, a very long string, your code, into a very large integer, the binary. And what it does is it applies successive transformation on this. So you have your code, right? It reads it, it parses it. So you have function 1, parse it into an AST. Then you have function 2 that does some analysis on that AST, make sure you don't have any mistakes like unused variables or using a variable that is not defined. That's your second function. Then you have a third function that takes this AST and then transform into some kind of intermediate language. And then you have a fourth function that takes this intermediate language and transforms it to binary. But what you're really doing is you have this pipeline and you have this input and you're applying successive. Excellent candidate for functional programming. A bad candidate for functional programming is user interface. What is a user interface? A user interface is typically a Windows desktop. You have all these Windows controls, right? You're manipulating them. So I have a drop-down menu. I have a state of what my system is. And each operation is doing nothing but manipulating that state, right? You could do that in functional programming, don't get me wrong. But typically, such a thing will be done better or more intuitively in an object-oriented language because the model fits that mental model, your application model fits that mental model for object-oriented language. So that's typically how you design. So I would generalize your question and say, think of any programming language or any kind of thinking and think of models of what kind of models fit that well and see your application in which particular model it's fitting. And that would help you decide which is a good candidate for functional and which is a good candidate for object-oriented.
Yeah, and I'd say that sometimes service has both models.
Yeah. True, and that's the reason why you have a microservice architecture is because you can have technology heterogeneity. So I can have something like some part of code written in F#, some kind of written in C#. In fact, F#, C# is not a problem. I can even have a monolithic with F#, C# because they get compiled into the same intermediate language. But you could have some code written in C++, and you could have some code written in F#, and they still will work fine. Because you may not want to use F# because, hey, you decided to switch from Java to C# and you have a legacy code in Java that works perfect and nobody wants to touch it. Sure, no problem. So having microservice architecture, having technology heterogeneity gives you that advantage. You can decide this is the language, this is the platform where this particular service fits best, and yet everything will work together with each other seamlessly.
Hello, I have a question about transaction. Could you please explain how microservices with event model can handle transactions properly?
Could you be more specific? What kind of transactions? Like,
for example, I withdraw something from my account, some value, and with event sourcing, it would be just event, withdraw something, and how to handle it in transaction manner? I mean, to commit transaction, to roll back if needed. If I don't know whether receiver gets my event or not.
Okay, good question. So actually this question is a little bit broad in nature. And what happens is that the answer goes in, typically in a monolithic you have a two-phase commit, right? That solves this problem. The problem with microservices is you don't have two-phase commits. And the reason is that you have all these services different, each one of them have these databases, so two-phase commit is not an option. So you use event-driven architecture, right? Why do you use event-driven architecture? The reason why you use event-driven architecture is because event-driven architecture allows me to have a service which is available and partition tolerant, but eventually consistent. Now you don't want to sacrifice availability of a service because non-availability or downtime costs you money, right? And in an ideal world, I would like to have all three things: consistency, availability, partitioning, but I know I can't. So you have to settle in with the model of eventual transition. Unfortunately, from a theoretical point of view, your problem is unsolvable. It is unsolvable even otherwise, actually, in a microservice architecture, no matter what you do, because of the very nature that you can't have consistency, availability. And if you're willing to forego availability and say, I just care about consistency and partition tolerance, or I don't care about partition tolerance, there are other solutions, right? So typically how it works is you make this transaction, and you see that all the time in bank. I withdraw money, I don't have that much money. It actually will send me an email after one day. By the way, you overdrawn on your account, please put up money. That's how you typically do it. In such a kind of architecture, what you do is you have an event and you have a way to reverse that event. So you would have basically a service that says, okay, I withdraw the money, generate an event, I withdraw the money. The second service that says, okay, I withdraw the money, but you don't really have that money, so I have to nullify this transaction. So it will generate a third event that says, nullify the previous transaction. So each time you have an event, you generate a new event, and uncommitting what you did before is also a new event. And the drawback with this approach is that it's eventually consistent, but it's not immediately consistent. So you don't have real-time feedback, right? You can't have it. But the idea is that generally it's going to be so fast, it's not 100% consistent, but it's 99% consistent. You get feedback within seconds, so it's usually not a problem. But to some extent, that is a known problem in microservice architecture in general, nothing to do with F# that you can't solve because of the limits on CAP theorem.